Alright, let's start with the basics. When we talk about a bottleneck in a process, what we really mean is a step that slows everything else down. And think of it like the narrowest part of a pipe, no matter how wide the rest of the pipe is. The flow will always be restricted at that point. In operations, this shows up when demand is higher than the capacity of a specific step, and as a result, you get delays, work pulling up in queues, lower efficiency, and longer cycle times overall. So, if bottlenecks are such a problem, the natural question is how do we deal with them? That's where process improvement comes in. The idea is pretty straightforward. Identify the step that's holding the system back, analyze why it's a constraint, and then remove or reduce its impact. By doing that, we can boost throughput, cut down on lead times, improve quality, and bring down costs. And let's pause for a moment. What actually happens if we don't tackle these bottlenecks? Well, from a time perspective, cycle times stretch out, deliveries get pushed back, and customers start losing trust because their expectations are not met. From a resource perspective, some missions or workers might be underused while others are overloaded, inventory piles up, costs climb, and workers often get frustrated. And on the business side, here, if you are constantly limited by these choke points, profitability drops, growth slows, and competitors can take advantage of your weaknesses. That's important. So,
So, what is a formal approach to dealing with this? One well-known framework is the theory of constraints, and it says every system has at least one constraint that sets the limit on performance. If you want to improve the whole system, you have to focus on that constraints. Okay, and here's the key formula from that theory. You can see throughput equals the minimum of capacity sub I. And what is that? In plain words, the system output is only as strong as its weakest step. And here is a warning. If you put effort into improving steps that are not constraints, the system as a whole won't improve. Okay, and there are also two other concepts worth keeping in mind. The first is Little's law, and what is that? It says L equals lambda times W, which means the average queue length equals the arrival rate multiplied by the wait time. That tells us that if things keep arriving faster than they are being processed, queues will grow. And the second concept is utilization. The formula is here: U equals rho over C, which simply means actual demand divided by available capacity. A high utilization rate often hints at potential bottlenecks. Alright, and once we understand bottlenecks, the next challenge is figuring out where they are. And for that, we have a few common identification methods. The first is value stream mapping. Here we create a visual map of the entire process. Every step, every flow of material or information, we mark which activities add value and which don't. Then we calculate cycle times, check where they are the longest, and pay special attention to where inventory piles up. A chart often helps highlight this. For example, when you see one step with both long cycle times and large queues, that's a strong indicator of a bottleneck. And for example, value stream uh, mapping, and here we can see our chart. Look at this: inspection, processing, assembly, testing, and shipping. So Another method is statistical analysis, and look at this. This is more data driven. We gather numbers on throughput, utilization rates, wait times, and queues. Then we look for the steps with the highest utilization. If you see utilization constantly above 90%, that's usually a warning sign. And statistical tools also allow us to analyze correlations and trends, making the findings more objective. And third method is simulation, and it is here. Instead of relying only on data from the live process, we build a model of the process in software. We can run multiple scenarios, adjust parameters, and see how the system behaves. This way, we can identify which resources get overworked and test what would happen if we, say, added another resource or redesigned a step. It is a safe and cost-effective way to experiment before making real changes. Okay, now theory and methods are good, but how does this look in practice? Let's go over some real-world case studies. First example, a manufacturer of automotive parts. Their production line was consistently falling short of daily output targets, only reaching about 75% of the goal. Analysis showed the welding station was the bottleneck. It had a utilization of 95% compared to an average of 65% for other stations. And let's look at this. So queue times at welding were about 45 minutes, and setup took 35 minutes per changeover, and quality issues were causing a 12% rework rate. The solution was multi-phase. They introduced smart techniques to cut setup time down to 8 minutes, added a second welding station to share the load, improved upstream quality checks to reduce defects, and cross-trained operators for flexibility. And the results were significant. Daily output jumped from around 750 to 1100 units. Setup times dropped by more than 70%. The quality rate went up from 88 to 96%, and overall efficiency increased notably. The return on investment was strong, over 3 times the cost within the first year. So, as you can see, bottleneck analysis is not abstract. When done systematically, it can have very concrete business results: higher throughput, better quality, lower costs, and improved customer satisfaction. The main point to remember is always focus improvement efforts on the real constraint, because that's what determines the pace of the entire system. So let's look at other examples for here: healthcare, project summary, and other example here. And final. So thank you for listening.